if we have uniformly accelerated motion, we have a velocity time graph that is a straight line. We said this before already, right? Okay. The area underneath it is the change in position of an object. We know this. So please derive one equation for displacement from the above graph, treating the area as a trapezoid. Well, hey, if we're treating this as a trapezoid, that means we're looking for V final, V initial, and delta t. And the area is, well, delta d. Although technically we should put all of these down as vectors. Okay. That would give us, well, we know that the formula for the area of the trapezoid is one parallel side plus other parallel side divided by 2, so the average multiplied by the height. So delta d equals V initial plus V final over 2 times. What does this give us if we decide to deal with it as a triangle on a rectangle instead? Well, that would mean we take this and put another line there. So what we would end up with is delta d is equal to V initial times time. Hey, this should look familiar because we covered this already before. Plus what? Well, okay, we have the change in velocity, which is equal to 1/2 delta V delta t. Now we know the change in velocity is equal to acceleration times time. So this would give us V initial delta t plus 1/2 acceleration times squared. Now, later on, you will find that a lot of the time you take out these deltas because having to draw so many additional symbols is irritating. But you should always remember that that's really only appropriate if you set the beginning of a particular time frame to be time 0. And that if the question obviously means delta t when it uses the variable t, yeah, please do so carefully with consideration. So, okay, what about all these variables put together? We have, 5 key equations. Okay, we already had 2 of them. And what are the characteristics of those 2? Well, we excluded one variable for each of the key equations. We list the key equations below, so we won't go back and mark which ones are excluded on those 2. What are the key variables? Well, we have V initial. We have V final. We have delta t. We have the area. And what's the 5th one? Oh, we talked about the change in velocity, which is going to be acceleration times time. So the 5th one is acceleration. Now for each of these key equations, we exclude one variable. So the final velocity is equal to the initial velocity plus acceleration times time. This excludes the displacement. And the next one is treating it as a rectangle and a triangle. Well, we have the change in velocity for the triangle, but we don't have the final velocity shown here. Now, what about this one here? Well, we start off with a big rectangle. So the final velocity multiplied by the time, and we subtract the acceleration times time times time times 1/2, because we remove this big triangle here, which excludes the initial velocity. Okay, what about this one? Hey, as we can see here, we treated it as a trapezoid and we did not give half a fig about the acceleration. Now the last one is the one that is most interesting, because hey guys, how do we get v final squared minus v initial squared to be equal to 2AD? What does this exclude? This excludes time. So how is this possible? Well, we know that the two velocities are related by the acceleration and time. Now we also know that the two velocities and time are related to distance. Of course, then there's something else we notice. We don't have vector symbols on top here. Why is this and how is it derived? Okay, guys. Well, say we're moving at some velocity, like say meters per second east. Meters squared per second squared, well, yes, okay, a square second is kind of a sketchy unit if you think about it too hard, but it could be per second, which is perfectly reasonable if we're, say, speeding up. But if you're telling me that you're driving in the direction of east squared, or that you're jumping up squared, I would be very, very suspicious for hopefully obvious reasons. So that's why this we treat as usually scalars, although we do pay attention to positives and negatives. They are very important. Now, how is it derived? Well, difference of squares says that f squared minus vi squared is equal to vf plus vi vf minus vi. So this is equal to 2a delta d. Okay guys, how did we relate a and delta d to vi and vf again? Here we have, well, let's substitute that in. So we have 2 times something, whatever a is. And then we have delta d, which is vi plus vf. If it was entirely up to me, I would have written this part in front, but I wanted to make sure that everybody can follow what becomes what. So for a, we end up with, so a delta t is equal to vf minus vi. And a is therefore equal to vf minus vi over delta t. Which means we end up with please remember vector symbols over delta t. Okay, so when we multiply, what happens? We cancel out the 2's, and we cancel out the delta t's. And vi plus vf is equal to vf plus vi. Yes, okay, we do have the, technically these are vectors problem. But hey, remember that when we were treating them as scalars, positive, negative are technically directions if you think about a number line for a while. So, what you end up with is, wow, left side equals right side. And therefore, QED, something like quod erat demonstrandum or something, i.e. what is asked has been shown. Obviously, that sounds a lot more dignified than, ha, there, proved it. Which is what it really means. Okay, example 1. A sports car enters a highway at a velocity of 25.0 meters per second south. If the car accelerates at a rate of 3.0 meters per second squared south for 5.0 seconds, what is the displacement of the car over this time? What is the speed of the car after the acceleration? Well, what formula should we use? Here we have, VI is equal to 25.0 meters per second south. If you are unsure about how to do a problem, start by listing out all your variables, or all the variables that you are given, and of course what you are being asked. Because knowing where you start is kind of useless if you don't know where you're trying to go, and therefore can't plot a course. Now, acceleration is equal to 3.0 meters per second squared south. And time is 5.0 seconds. And what are we looking for? We're looking for we want delta D. Or you could say delta D equals question mark. Okay. How do we link these four variables? Do we have a specific formula that allows us to do so right away? Well, yes. All those 5 formulas, they use 4 variables out of the 5 that can possibly be involved, and they exclude the 5th. So if you're given 3 variables, you can find the others. Delta D is equal to, how do we think of this? We think of this as a trapezoid problem. And wait a second. In this particular formula, we use a triangle and a rectangle instead of just a trapezoid, despite the fact that the overall shape is the same. So we have VI, we have AT, or A delta T. Often you see this abbreviated off, the delta part. If you're doing a quick and dirty sketch, if you're being asked to show all your steps in great detail, like you will be when you're just starting out, please do show everything in great detail. Okay, so we have VI delta T plus 1/2 acceleration delta T squared, which is equal to, one of the ways that you can make sure that you're getting everything correctly is check the units. If you want meters, then, well, VI is in meters per second. We multiply by seconds. The seconds cancel out. This term comes to meters. Okay. And what about this term? Oh, meters per second squared multiplied by seconds squared. Hey, that cancels out to just meters. Therefore, our units are correct, which is usually a pretty good indicator that you are at least on the right track. Okay, so VI was 25.0 meters per second, and time is 5.0 seconds plus 1/2. A was 3.0, and time was 5.0. And then we square that. So this is equal to 25 times 5 is 125 plus 1/2 of 3.0 times 5.0 squared. 5 squared is 25. Times 3 is 75. And then you divide by 2. Okay, this gives us 125 plus 37.5. How can we do this without adding each digit? Well, 37.5 is 25 plus 12.5. And 125 plus 25 is 150 plus 12.5, 162.5. And this is in meters. In which direction? South. We are treating south here as a positive direction. If, say, the acceleration had been north instead, i.e. the guy has to slow down for whatever reason while entering a highway, possibly because of a traffic jam, then you would see the A being given as negative however much south. Or we could have set north as a positive direction and VI could have been negative, but well, that gives us displacement is negative whatever in some direction, which is a little bit not as useful as we'd like, because if you keep on telling some guy, oh, we're going negative 100 meters to the north, they're going to ask you, why don't we just say 100 meters south instead? And it would be a good point. So this is south. And what is the speed of the car after the acceleration? So, if we want to relate these variables, we have v initial, we have acceleration, and we have time. V final is equal to v initial plus acceleration times time equals 3.0 times time, which is 5.0. So 25.0 plus 15 is equal to 40. And this is given in meters per second south. There's a bit of a problem with this number, which is that you're going at 144 kilometers an hour. Yes, this is legal in some areas, but in many others, well, not so much. Okay, there is another issue here. Hey, by significant digit convention, this is 2 significant digits, this is 2 significant digits, that one's 3. You can only go by the least number of significant digits in the variables that you actually used, which in this case would round this to 1.6 times 10 to the second meters south. We say that displacement was 162.5 meters south, and final velocity was 40 meters per second south. The significant digit convention is used in many relatively formal occasions, so honestly we should say that significant digit convention even at the Olympiads you use significant digits. At least last I remembered. The final velocity is the same, but the displacement is 1.6 times 10 to the second meters south. Yeah, I know it sounds kind of awkward and irritating, but, well, it's a convention. Okay, that's a statement which basically restates what the question asks and then fills in the answer that you got. Statements are expected for all word problems, but for time purposes, we will omit some when we're showing examples here. Please do not omit statements when you are being asked word problems in class, on a quiz, on a test, and so on.